Alright, welcome back. Module 15, Part 2, looking at the lab. So, the basic flowchart for our system is provided here. So you got our physical signal, so that's our infrared signal getting sent out, and then the intensity of that signal as it comes back gets converted into an electrical signal, so a voltage. So your continuous electrical voltage, depending on how strong, and obviously the closer you are to an object, the stronger that reading comes back. And we got 10 to 80 centimeter range for these IR sensors. That electrical signal gets passed through a low pass filter to remove aliasing capacitor that's actually through the board. If you take a look where the bottom right of your board, where we're going to be connecting those IR sensors, we're passing them through a low pass filter, and then eventually we're going to take the output of that low pass filter, which we're then going to run into the board. That is going to run through 3 different pins. We're going to be connecting the right signal to pin 90. So we have our robot, the front of the robot, so your LCDs back here. We got left, center, right. I don't know what right's so much larger for me. Boom. All right, and then the right one is connected to pin 90. The center is connected to pin 6-1, and then this guy is connected to pin 9-1. Okay, so then what we see is those pins. If we can look down here, let's look at 6-1. You can see that's going to an ADC 14, a 14-bit ADC, specifically module 14. Remember up here we take a look and we said we had 24 channels. So this is going to be channel 14. Pin 9091 are down here, also connected to the same 14-bit ADC, but they're connected to channel 16 and 17. So that's our ADC. We're going to take that output, that digital signal, we're going to pass that through a digital averaging low-pass filter. That's going to provide us a nice clean signal that's going to come out of there. We're going to take that filtered signal, we're going to convert it. So this is going to take our raw digital to distances that actually mean something. So 30 centimeters from the wall. That's going to go into our controller, and our controller is going to be the one making decisions, is that too close to the wall? Should I stop? And then it's going to change the PWM that provides to the motors. So this is the basic flow chart. This is, I'm going to bust out the rainbow pin. Ooh, whoa, I didn't know there's other choices. Space pin, that's how important this is. Okay, we got the space pin now. We're going to increase the lifelong debate between the red pin and the rainbow pin, and we're throwing the space pin. All right. So key thing to note are these 3 modules that we're using. We're going to see that in the code. We're going to see that we're connected to those different channels. And then, like I said, the pin 6-1 is the center, 17 is the right, and this is the left. I'm digging this space pin. All right. And that's what we're going to have to make sure we configure when we start off the So we're going to go through each of these steps. So this stuff all done on hardware. So obviously we have our sensor. We have a built-in capacitor on the motherboard. Built-in filter on the motherboard. And then we come through to the MSP432. We got the analog to digital converter. We got the low-pass filter. We have our convert function, which we are going to write, and the controller, which we will write as well. All right, so let's talk about how to initialize these ADCs. And this is going to be a little brutal, but we'll get through it. So this is going to be very similar to when we did the PWM. Texas Instruments provides you an example. We're going to talk about what's going on in that example. We're going to kind of throw out some of the most important things here. And then you're going to implement this for our specific channels, 17, 14, and 16. And then we will use that to test program 15.1 to make sure that things are working how we expect it. All right, so again, this all comes back to our data sheet, specifically that SLAU. I can't remember, it's 356 or 365. It is 356H. This is chapter 22, which is the ADC 14, the analog to digital 14 converter 14-bit. All right, so this is, you're gonna have to go in there this time, and you're gonna actually take a look at these registers and figure out how am I going to, what values do I need to set. So I'm going to tell you what we're going to set these to. So the first thing we're going to do, and we do this often, is we are going to disable the ADC 14. So step 0, disable, and that's going to be in the CTL 0. Specifically, it's bit 1 to disable it. And we always disable the components we're trying to set the settings for, so that way we don't cause any issues if something else is using it. All right, so if we take a look at the control register, that is going to be the CTL 0, which to CTL 0 and CTL 1. Let's take a look at CTL 0 first. Bring the red pin out for the fan. The fans. All right, we're going to divide by 1, pre-divide by 1. We're going to have the, we're going to use the, whoa, get attacked over here. ADC 14 software control bit. So the analog digital converter has some capability to get triggers from external sources. We're going to use the software control. So, and both of these two, the SHS and the SHP, are setting those. This one's going to be the sampling timer. So as you can see, I'm not giving you the exact bits you're going to use. You're going to have to kind of go in there and take a look. All right, let's see. We're going to not invert it. So this talks about inversion. No headstands here. We're going to, again, divide by 1. We're using SMCLK. All right, this next one, so the sequence mode select. So basically, if we're using only one channel, then it would be a single channel, single conversion, or if we're using multiple channels, it's going to be a sequence of channels. So what you're going to see in the labs, first you're going to do ADC 14 by itself. That's going to be program 15.1. So that's going to be single channel. But then for the actual application, we're going to use the ADC 17, 14, and 16. That's a sequence. So we're going to use both a single and sequence. All right, busy. We're going to start off by waiting so we're going to disable it. We're going to make sure it's not busy anymore. So that's one of those while ADC, that bit is a 1, we do nothing. And then once it's a 0, then we're going to be continue on changing up our CTL 0. You'll see it in the comments of the code. It's very straightforward. All right, so we're going to take these 3 guys, actually just these 2 first. And we're going to set it to 32 bits, or sorry, 32 clocks and 32 clocks. So what that's going to do is it's going to have 32 clock cycles. It's going to sample 32 clock cycles, hold those values, and then average those to provide 1 reading. So that's another nice little filtering capability built in that we're going to take advantage of. We're going to use 32 pulses and 32 for both of those. All right, so let's see. We're going to set MSC to multiple. So basically, it's going to take 1 first rising edge, and then it's going to sample continuously. So we're not going to have keep having that software trigger keep triggering. So it's going to be the it's just going to be the 1. It's going to be a 1. Okay. All right, 6 to 5 reserved on. We're going to power it up. It's going to be disabled to begin, and then we're going to and we're not going to start it. Not started yet. Okay, so that's our CTL0. Going down to CTL1, our control 1. The big things we're going to change in here is where we're going to store information, what kind of resolution, what format, and then what's our power source. So looking at, these are going to just map normal, so we're going to leave those as 0s. We're not going to change anything in there, but the BAT map bit 22, yep, we're going to leave that one as well. Yep, sorry, all of these. Leave. I'm not going to change those. Our starting address, so we are going to use ADC 14, which ADC 14 stores the results, so the actual digital values in ADC mem, and based off the channel. So we're using, actually you get to choose where you want to store it. We're going to store it in ADC 14 mem 2, 3, and 4. So when it says the start address, we're just going to start at 2. Resolution, we want 14-bit resolution. The format is going to be binary unsigned. And the reference is going to be on continuously, so we're not going to burst. And then the power is going to be regular power mode. All right, and the MCTL, that's where we're actually going to assign ADC 14 mem 2 to, let's see, double check, this is going to be channel 17. So we leave everything the same except for this last bit. And by leave everything the same, we just set them to 0, sorry. And then this last bit is going to be set to which of these channels we're storing in. Alright, and so the ADC ADC14, so the 14-bit analog digital converter, channel 17 is going to be mapped to memory 2. So we take MCTL2 and we just take this last 4 bits and we're going to map it to the specific channel. And if we take a look at the register, we can see it's going to set, if it's using A17, it's going to be 10001 in binary or just 0x11. And then we can go through and assign those for each of the different MCTL3, which is channel 14, MCTL4, which is channel 16. And that's where the data is going to be stored. Okay, so how does this all work? So basically, at a certain rate, we're going to sample the analog or turn on the analog to digital converter at a certain rate, and that's going to be based off of here it shows sys handler. That's incorrect. It's going to be timer A1. We're going to run timer A1 at a certain rate. It's going to call the analog to digital converter. So basically, as long as it's, so we're going to wait for it to, while busy, so while that's a 1, we're going to sit there and wait. Once it's not busy anymore, we're going to set that CTL0, that's 0 most bit, which if we go back to the data sheet, that CTL0 bit is the start conversion. And that's going to go through at the SMCLK, that 12 megahertz. It's going to take 32 bits, 32 clock cycles, and then it's going to sample that, and then it's going to provide you the, and then so while it is busy, while there's no data, basically what that guy's saying. So the IFGR registers where it's going to store the data. It's going to be the flag saying the data is ready. So IFGR flag telling if data is ready. Once it is a 1, then you're going to store that value into, the results stored in the memory address. For us, it's mem 2, 3, and 4. We're just going to return that value. So we're going to have to do this 3 times for us. We're going to have to do it left, center, and right. And then we're going to run that through the digital filter. We're going to tell, we're going to set our semaphore saying that, hey, the ADC is done, here's our data, go forth and conquer. So this is actually sampling the ADC. So if we go up here, back to our chart, this is the time in the X direction. So we're going to be running that at 0.5 milliseconds, or I think that's about 2000 hertz. If I go down here to take a look, yep, 2000 hertz. Boom, nailed it. All right, I do know what I'm talking about, I guess, sometimes. But we're going to be running timer A1, not sys handler. And that's going to be going on in the background, right? Timer A1. So the in the background, every 0.5 milliseconds, timer A1 is going to run. We're going to sample the ADC using our little ADC helper here. Then we're going to come back and provide that information to our controller. So that's just getting the information. That's getting a digital value, a raw value. It's going to be a value between 0 and whatever 2 to the 6. I can't remember what 2 to the 16 is. That's not very helpful. That's just but we can take that value now and convert it to a distance. And we do that based off the data sheet of the actual GP2Y0A21YK0F distance measuring sensor unit. So basically, if we take a look at that graph, I did not provide it here, but it's really easy to draw. Let me just pull it up real quick. So they characterize these sensors, they're tested a lot, and then they provide a signal. So if we take a voltage here, and then we have centimeters here, then our signal is going to look like this. It's going to be a little bit more rounded. So, all right, perfect. And we can take now and take the inverse of that, and it's going to provide us a different graph that's going to look like this. This is voltage in 1/centimeters. And then we can take the trend line, and that trend line is going to be a linear equation. We can solve for different variables to then determine our distance equation. And that's what you're going to do. So if we take a look at C is a constant. That is just the distance between the center of your robot and each of your distance sensors. So I'll provide you guys a measurement tool in millimeters that is going to allow you to determine, hey, how far are those sensors from the center of my robot. I think it was about 60 millimeters, something along those lines. And then you're going to use the equation to solve for A and B, which are they're characteristic constants for each of the sensors. So it's going to be different for each of these three sensors. That's why there's an AR, a C, and AL. There's going to be a different characteristic constant that we're going to use. And the way we're going to do that, so we're going to have these, so there's a wall, we're going to have lines going away from the wall. The lines are going to be measured. So let's just say this is 0.25 meters, 0.5 meters, 0.75 meters, and 1 meter. All right, you're going to read the values. Program 15.2 is going to print the actual raw ADC values. So at 0.25, it might be 1,000, whatever. 0.5 might be 2,500. Doesn't matter. We're gonna print. We're just going to take the distance and the actual raw ADC value. We're gonna graph that guy. Hopefully, it looks something along these lines. We're then going to take the inverse. So these are provided to you guys. There's a irdistance.xls that's in the lab. Both of these graphs will be made for you automatically. But then what you need to do is you need to add a trend line. So we're going to graph ADC versus inverse distance. Then we're going to add the linear trend line with an equation to our graph. We're going to format it so it's easier to read. We're going to change it to scientific with 4 decimal places so that it looks along the lines of that right here. So that's going to be 1/d. You need to solve for d. You got to do some algebra. It's going to be really tough. And that's going to give you your equation now that is in the form of d equals a over n plus b, which is going to be our equation here. So then now you can take a equals whatever that value is, and b equals whatever that value is, and those are your calibration coefficients. Super straightforward. We're going to do this in the lab the first day. Pre-lab, obviously, probably going to be setting up the registers. In the lab, first day is going through and calibrating, and then the last day we'll have probably 2 days to calibrate and get the actual sensor distances printing on your LCD. Alright, so I said that the timer A1 is going to be calling the ADC at about 2000 hertz. So it brings us back to this equation that we've seen multiple times now. So the reason we're bringing this equation in again is that the timer A1 counts at a rate of 2 microseconds, and we want it to count 250 times. So we're going to set 250 as our CTL0 or CCR0, and it's going to count down, 250 minus 1, count down to 0, and then that should take then 0.5 milliseconds. Alright, so when you initialize your timer A1, use that value, and I guarantee you're going to see something along those lines on a GR. Hey, if I give you this value, and I want this period, what are you going to input into your CCR0? So hopefully you guys understand what that is doing by now. Alright, that's all I got. That took a lot less time than I thought it was going to take, which is awesome. So we'll see you next time.